everyone, thanks so much for clicking onto the video. And today's learning objectives are to understand that the effect of temperature on the position of equilibrium is explained using a change in the value of the equilibrium constant, and to understand that the value of the equilibrium constant is not affected by changes in concentration or pressure or by the addition of a catalyst. So there are three very important things to remember about Kp. And the first is that it's only affected by temperature and pressure. So when we alter the concentration, then it isn't affected. So the Kp stays as the same value. The second is that we can predict the qualitative effects of changes in temperature on the value of Kp. And then for number three, a catalyst has no effect on the Kp. Please note that increasing the pressure or temperature on a gas phase reaction will increase the rate at which equilibrium is reached. So, explaining in more detail, for number one, for example, if we had the Haber process, so we've got 3 hydrogens and that's added with a nitrogen to form 2 ammonias. This is an exothermic reaction, so it has a negative enthalpy change of minus 92 kilojoules per mole. So if we increase the temperature of this, then by Le Chatelier's principle, the equilibrium would shift to lower the temperature, and it would favour the endothermic reaction because that takes away the heat energy. And so it would favour the reactants, the back reaction, if we increase the temperature. So looking at Kc, so looking at Kp is equal to the partial pressure of the ammonia squared over the partial pressure of hydrogen cubed multiplied by the partial pressure of nitrogen. So if the equilibrium has favoured the back reaction, that means that the bottom of the fraction will be a lot bigger than the top, and so Kp will be quite small. So if we increase the temperature, then Kp will be small. And the opposite of that is true as well. So if we decrease the temperature, then the equilibrium will shift to increase the temperature by Le Chatelier's principle. And so it'll favour the exothermic reaction because that gives off heat energy, and so favours the forward reaction, so it shifts to the right. And so we get more products, so we get a bigger value on top of the fraction for Kp compared to the bottom, and so the Kp is big. So when we decrease the temperature, the Kp is big. And now when we look at pressure, first we count up how many moles of gas we have on each side. So on the left we have 4 moles, and on the right we have 2 moles. And so that means that when we increase the pressure, because the equilibrium shifts to decrease the pressure, it favours the side with the least moles. So that means it shifts to the right, so it favours the forward reaction. And so we get more product, so there'll be a bigger value on top of the fraction for Kp, so Kp is big. So if we increase the pressure, then we have Kp as a big value. And then when we decrease the pressure, the equilibrium shifts to increase the pressure. So it favours the side with the more gas molecules, which is the left-hand side. And so the equilibrium shifts to the left. And so there are more products, so the bottom of the fraction for Kp is bigger, and so Kp is small. So we have that when we decrease the pressure, then we have a small Kp value. And so this also explains number 2 about the temperature. And then for number 3, a catalyst has no effect on the Kp, and that's because a catalyst just speeds up the reaction. So it speeds up the forward reaction and the back reaction by the same amount, and so they cancel out, so overall it has no effect on the Kp. And so Kp can be changed by either changing the pressure or the temperature, and Kc can only be changed by changing the temperature. So the gaseous reactants W and X were sealed in a flask and the mixture left until the following equilibrium had been established. For A, write an expression for the equilibrium constant Kp for this reaction. And so what we do is we know that Kp is the ratio of partial pressures of the reactants to the partial pressures of the products. So we have the products on the top and the reactants on the bottom. So Kp is equal to the partial pressure of Y, and this is cubed because we have 3 moles of it, and we multiply that by the partial pressure of Z squared over the partial pressure of W squared multiplied by the partial pressure of X. And that's our expression. So for B, state one change in the conditions which would both increase the rate of reaction and decrease the value of Kp, and explain your answers. So first let's think about Kp, and we know that only 2 things can change the value of the Kp, and that is either changing the temperature or the pressure. And that's because if we change concentration and use a catalyst, it doesn't change the value of Kp. And so we've only got 2 options. And first let's consider pressure. So pressure does change the value of Kp because increasing the pressure shifts the equilibrium to favour the side with the least amount of moles of gas to decrease the pressure. But it doesn't increase the rate of reaction. In fact, it doesn't change the rate of reaction at all. It just makes the equilibrium shift to either the left or the right to favour the products or the reactants. And so the answer must be temperature. And so let's have a look at the reaction. So we see that the forward reaction is exothermic, and that's because of this negative enthalpy change. So we know that heat is given out, so it's exothermic. And so if we increase the temperature, then what happens is that the equilibrium shifts to decrease the temperature. So So what happens when we increase the temperature is that the equilibrium works to decrease the temperature. And so it favours the endothermic reaction. In this case, that is the back reaction. And so there are more reactants formed because the equilibrium has shifted to the left. And so because there are more reactants which have been formed, that means that the value of the bottom of the fraction for Kp is much bigger. And so our value for Kp decreases. So the first thing to say is that when we increase the temperature, then what happens is that the equilibrium works to decrease the temperature. And it does this by favouring the endothermic reaction. Favours endothermic and in this case that is the back reaction. So we know that equilibrium shifts to the left, and therefore we have more reactants, and so the Kp value decreases. And now we need to discuss why an increase in temperature will increase the rate of reaction. And that's because when we increase the temperature, we supply the gas molecules with more energy. And this is kinetic energy. And this means that the particles collide more frequently. So there are more collisions per unit time. And this also means that more of the particles, a bigger proportion of the particles, will have the activation energy needed for a successful collision, so to react. So a bigger proportion of particles have the activation energy, or an energy bigger than the activation energy, so they can successfully react. And so we have more successful collisions per unit time. And so overall, that means that we have a higher rate of reaction. So before I get started with number 2, feel free to pause the video and to try it out yourself first. So in the below expression, what would happen to Kp if the temperature would decrease, more of A was added to the mixture, and a catalyst was added? And so first, let's write down our expression for Kp. So for this, our expression for Kp would be equal to the partial pressure of C multiplied by the partial pressure of D over the partial pressure of A multiplied by the partial pressure of B. So then for A, if the temperature would decrease, the equilibrium would move to increase the temperature, and so it would favour the exothermic reaction. Now we can see from this delta H here that the forward reaction is endothermic, and so if the temperature would decrease, then we would favour the exothermic reaction, which would be the back reaction. And so the equilibrium shifts to the left, and so more reactants are formed. And because there are more reactants formed, that means that the bottom of the fraction for Kp is bigger, and so Kp decreases. And then for B, if more of A was added to the mixture. Now, the really important thing to remember about Kp is that only two things can change the value of it, and that's either the temperature or the pressure. And adding more A means that we're increasing the concentration of A, and so that means that it doesn't change. And then for C, you need to remember the same point. So only pressure and temperature can change the Kp, because what happens is that a catalyst speeds up both the forward and the back reactions by the same amount, and so overall it cancels out. So there is no change to the Kp again.